Welcome. This video is an introduction to the technique of integration using partial fractions. For this technique, we are focused on integrals only of rational functions. This technique only applies to antiderivatives of rational functions. The idea behind this technique is to take a given rational function, which is a polynomial divided by a polynomial, and to break up that fraction into smaller fractions called partial fractions. This is the reverse of a technique that we're familiar with. This is the reverse of fraction addition. So instead of adding fractions together, we're looking at taking one single fraction and splitting it up into a lot of smaller fractions. We're going to work through an example, but we won't work through all of the details. We'll just see why this technique is useful, and we'll get a glimpse of the sorts of problems that this technique helps us to solve. So for this example, we'll look at this integral. We have a rational function. It's rather complex. It's 4x to the 5th minus 19x to the 4th plus 33x cubed minus 30x squared plus 23x plus 6, all divided by x to the 4th minus 4x cubed plus 5x squared minus 4x plus 4. That's complex. Now, this single fraction, using the technique of partial fraction decomposition, can be broken up into the following expression. This is equal to 4x minus 3 plus the fraction 2x divided by x squared plus 1 plus 3 divided by x squared plus 1 minus 1 over x minus 2 plus 4 divided by x minus 2 quantity squared. Now, we're glossing over lots of details here. There's a whole procedure for taking this fraction and splitting it up into this sum of smaller fractions. This is what fraction decomposition is all about. We're just interested in looking at this result that we get and seeing how fraction decomposition helps us to solve the integral. Let's try to solve this integral now that it's been decomposed for us. The antiderivative of 4x is 4x squared divided by 2. The antiderivative of the negative 3 is negative 3x. And then this fraction 2x divided by x squared plus 1, this can be solved using u substitution. If we use u equals x squared plus 1, we won't work through all the details, but the antiderivative of this fraction is natural log of the absolute value of x squared plus 1. And we could check by taking the derivative that this is indeed the correct antiderivative. This next fraction, this is a rather less known expression, but the antiderivative of x squared plus 1 is the arctangent of x. So this fraction has an antiderivative of 3 times the arctangent of x. This fraction, this can be solved using another u substitution, where we use u equals x minus 2. Again, we'll skip the details, but this has an antiderivative of natural log absolute value of x minus 2. And this last fraction, we'd want to view this as 4 times x minus 2 raised to the negative 2 power. Once again, we would do a u substitution, u equals x minus 2. And the antiderivative of this final fraction is minus 4 divided by x minus 2. All of this plus c. Now, I realize that we're glossing over lots of details. We didn't even discuss how this partial fraction decomposition is performed. But the main idea behind this technique is that we can split up one big fraction into many smaller fractions, and then individually for each of those smaller fractions, we apply appropriate integration rule, and we can find the answer.